Complicated example. We're interested in what the volume is when we rotate g of x around the line y equals 10. And so, if you look at our previous example, basically we're interested in finding here the area under f of x, and we just did the integral from a to b of f of x dx here. I just left a blank to enter the function. So what the integral basically does is it takes the operation, in this case f of x, and it applies it to all the many values as it iterates between a and b, and then it adds this infinitesimal width, w, as represented in the integral by dx. And so that's how it works when we're trying to make rectangles. So basically, it does the operation, which is just a line, and it adds width to it. Well, see, now the only difference is now we're trying to revolve this function around a line, which is not going to form rectangles, it's going to form circles. So what it would look like is we made our first circle here. Going into the screen, it would make a circle if we rotate it around. And the idea is that the integral will add this infinitesimal width to each of these circles to make each circle a cylinder, a really thin cylinder, and then it'll basically calculate as many cylinders as possible between A and B as possible. And so before, if we look at before, we're basically for each operation, the integral, so for f of a, for the function value at a, the integral adds this width value here. And then for a plus w, this point a plus w, the integral multiplies by width to make it into a rectangle from just a line. So if that's how this works, then over here, if I were to pull down here, I wrote down the same sort of formula. And so there's some formula that the integral will do here for all these infinite number of values between a and b, where it applies some width to some formula, and then that you can express that as the integral of that formula. So what would the formula be? Well, let's let a equal the area of a circle, of one circle of our drawing, of any generic circle. And we can even say a of x. So a of x, because the area is a function of what value between a and b we are. And so let's look at the very first circle here if we were to draw. The radius of the circle, it's centered at y equals 10, and the radius, if we were to drop down all the way to the function, well, the value here at the function is f of a, right? And then the value up here at the line is going to be y equals 10. So y equals 10. So the value of the first circle would be 10 minus f of a. The value of the second circle, if we were to add like a width in here, the next circle would be f of a plus w, right? And so you just keep going as you get to larger and larger values here, and the integral is just adding width to each circle. And so the formula for a circle is pi r squared, but in this case the radius is always going to be 10 minus the value of our function, which is, I'm sorry, this should not have been f, this should be g. I'm sorry. 10 minus, so it would be, alright, so this is the radius, pi is on the outside here, so 10 minus g of the function value, that's squared times pi. That's the value of all the circles we could have between a and b. And the integral, so we'll apply that to each circle. We'll apply a, so a value at a, which will be the area of the circle at a value at a plus w, which will be the area of circle one width away from a, and then so on and so on, all the way until we get to the last circle right here, which would start, sorry, this is a bad drawing, but it would start at b minus 1 width. And the integral, so then the operation we're performing is the area of each circle, and the integral adds this infinitesimal width dx to each circle to turn them into little cylinders that get infinitely small, giving us infinite number of circles, giving us an infinitely good approximation of the area of the volume around when g of x goes around y equals 10. So Hopefully that solves that. Oh, and then if you were to write this out, integral from a to b of, well, a of x is equal to pi times 10 minus g of x